At the dawn of 2022, the Hubble Space Telescope made a historic discovery, unveiling the farthest star ever observed by humanity. Dubbed Arundel, meaning morning star in Old English, astronomers marveled at this celestial marvel. When the Webb telescope succeeded its predecessor in 2023, it continued the mission of exploring this ancient star. Through the lens of Webb's near-infrared camera, NCAM, Arundel revealed itself as a massive B-type star, twice as hot as our Sun and radiating a brilliance 1,000,000 times greater. Speculations arose that Arundel might belong to the earliest generation of stars, born in the aftermath of the Big Bang, igniting a renewed fervor within the scientific community. Located within the Sunrise Arc galaxy, Arundel resides an astonishing 12.9 billion light-years away, existing merely 900 million years post-Big Bang. The relentless expansion of the universe has propelled it to a staggering distance of 20.28 billion light-years from Earth. Gravitational lensing, a cosmic phenomenon bending the fabric of spacetime, enabled both Hubble and Webb telescopes to detect Arundel. March 30, 2022 marked NASA's announcement of Hubble's discovery, revealing Arundel's presence behind the gravitational lens crafted by the massive galaxy cluster WHL 01378. Webb, equipped with similar capabilities, continued the pursuit, leveraging the gravitational lensing effect of the BHL 137D08 cluster to observe Arundel. Its magnification, estimated at over 4,000 times, transformed this distant star into a brilliant beacon, surpassing the brightness of its galactic surroundings. Unlike other celestial features, which often exhibit multiple images due to gravitational lensing, Arundel appeared as a solitary point of light, emphasizing its singular presence amidst the cosmos. Arundel's discovery shed light on the intricacies of star formation in the universe's infancy. With a potential mass ranging from 50 to 100 times that of the Sun, it likely succumbed to a supernova explosion within a few million years of its formation. Its scorching surface temperature of approximately 20,000 K hinted at its classification as a population 3 star, composed primarily of pristine hydrogen and helium, remnants of the Big Bang's elemental forge. While Webb's observations did not reveal any immediate companions to Arundel, astronomers speculated the existence of a cooler, redder companion star, undetectable by Hubble's instruments due to the expansion of the universe stretching its light beyond visible wavelengths. Arundel's classification as a B-type star, known for their luminosity and relatively short lifespans, further fueled speculation about its origin and fate. The accidental appearance of Arundel, though brief, sparked a revolution in astrophysics, offering a tantalizing glimpse into the universe's infancy. As astronomers continue to unravel its mysteries, Arundel stands as a testament to humanity's insatiable curiosity and relentless pursuit of cosmic understanding. Webb's observations of Arundel unveiled unprecedented details about its surroundings within the Sunrise Arc galaxy. The high-resolution images captured by Webb's near-infrared camera, NCAM, depicted a rich tapestry of cosmic phenomena, including regions of active star formation and ancient star clusters. The gravitational lensing effect of WHL 01378 magnified these features to an extraordinary degree, providing astronomers with a unique window into the galaxy's past. In addition to Arundel, Webb's meticulous observations revealed another gravitationally lensed star, named Quilla, situated within the same galactic ensemble. Quilla, a red giant star observed approximately 3 billion years post-Big Bang, offered further insights into the early universe's stellar population. The presence of such ancient celestial bodies underscored the dynamic interplay of cosmic forces that shaped the cosmos in its formative years. The Sunrise Arc galaxy, characterized by its high magnification due to gravitational lensing, showcased a diverse array of stellar phenomena. Webb's near-infrared spectrograph, NIR-SPEC, facilitated detailed analyses of the galaxy's spectral signatures, unraveling the chemical composition and evolutionary history of its constituent stars. These observations provided astronomers with invaluable data to reconstruct the galaxy's timeline and unravel the mysteries of its formation. As astronomers delved deeper into the data collected by Webb, they uncovered tantalizing clues about Arundel's physical properties and evolutionary trajectory. Despite its staggering distance and magnification, Arundel's classification as a B-type star hinted at its colossal size and luminosity. The absence of detectable companions challenged conventional models of stellar evolution, raising intriguing questions about Arundel's solitary existence amidst the cosmic expanse. The accidental appearance of Arundel served as a catalyst for groundbreaking discoveries, pushing the boundaries of human knowledge and understanding. With each observation, astronomers gain new insights into the early universe's secrets, unraveling the mysteries of star formation, galactic evolution, and the cosmic tapestry that binds us all. As Webb continues its mission of exploration, astronomers eagerly await the next revelation, poised to unlock the universe's most profound enigmas and illuminate the darkest corners of space. Arundel's luminous presence serves as a beacon of discovery, guiding humanity on its quest to unravel the mysteries of the cosmos and uncover the hidden truths that lie beyond the stars. Other known as OB associations, which are associated with giant molecular clouds, the Orion OB1 association is a spiral arm belonging to the Milky Way. Brighter stars make the spiral arm appear brighter, although there aren't many stars there, and it encompasses the entire Orion constellation. In addition, the classification scale includes 7 other categories: O, B, A, F, G, K, and M. O-type stars are extremely hot and luminous, with a color close to blue. Neo Zeta Puppis in the constellation Puppis shines about 1 million times brighter than the Sun. These stars exhibit distinct ionized and neutral helium lines and faint hydrogen lines. O-type stars emit most of their radiation in the form of ultraviolet rays. The majority of the first-generation stars are predicted to be of O-type. A-type stars are more common among observable stars with the naked eye. Denbin, the Ceres constellation, is an example of a highly active A-type star, while Sirius in the Canis Major constellation is also an A-type star but less active. A-type stars appear white. Many white dwarf stars also belong to the A-type category. They exhibit strong hydrogen spectral lines and lines from metallic ions. F-type stars are also active stars but tend to be main sequence stars, such as Beta Virginis in the Virgo constellation. Their spectra are characterized by faint hydrogen lines and lines from metallic ions, giving them a slightly yellowish-white color. G-type stars are the most common spectral type. G-type stars are perhaps the most well-known because the Sun belongs to this category. They have weaker hydrogen lines than F-type stars but, along with lines from metallic ions, also have neutral metal lines in their spectra. Supergiants are typically O or B-type blue or K or M-type red stars because they are so. It is unlikely for them to be G-type since these are unstable regions for supergiants to exist. K-type stars are orange-red stars with a temperature slightly lower than that of the Sun. Some K-type stars are giants or supergiants, such as Arcturus, while others like Alpha Centauri b belong to the main sequence. They exhibit very weak hydrogen spectral lines, if any, and mainly show neutral metallic lines in their spectra. Moving on to M-type stars, they are the most common spectral type in terms of the number of stars. Over 90% of stars are red dwarf stars like Proxima Centauri. Some giants, supergiants like Antares and Betelgeuse, and variable stars like Mira also belong to this category. The spectra of M-type stars are characterized by molecular and neutral metallic lines but usually lack hydrogen lines. Titanium dioxide may be abundant in M-type stars. The redness of these stars can sometimes lead to confusion regarding their actual distance, making them appear farther away than they are. If an object with a similar temperature, such as a hydrogen lamp, 3000 K, is placed a few kilometers away, it will also appear as a red light source to an observer. Similar to these stars, each of these spectral types provides valuable information about a star's temperature, luminosity, and composition, aiding astronomers in understanding the characteristics and evolution of stars throughout the universe. The Harvard spectral classification is the most common and easily understandable method of star classification to date. Additionally, astronomers classify stars based on their evolutionary stage and formation processes. Most of the stars we know today belong to generations 1 and 2. Stars of generation 3 have nearly disappeared or are extremely challenging to observe as they are at the boundaries of the Big Bang, where modern space telescopes struggle to observe. Therefore, cases like Arundel are exceptionally unique. Category 3 stars, without a doubt, Arundel is undoubtedly one of the first stars contributing to the era of reionization. Going back to observe the first 380,000 years after the Big Bang, the universe was a hot mixture densely packed with protons, electrons, other elementary particles, and light elements. Shortly thereafter, the expanding universe was rapidly cooling. Once the temperature dropped to around 4,950 degrees Fahrenheit, 230 degrees Celsius, protons and electrons could form atoms. However, not all elements were formed during this time, only hydrogen and helium, with oxygen notably absent. Hydrogen and deuterium isotopes accounted for about 3/4 of all atoms, while a few isotopes of helium made up the majority of the remaining quarter. A small fraction, about 1 part per billion, of lithium also formed. In reality, the first luminous objects did not appear until the universe was about 100 million years old, so for a period longer than the extinction of dinosaurs on Earth, there were no stars, galaxies, or any objects emitting light. The origin of the first generation of stars is known as population 3 stars. Their light is now too faint to be detected by current observatories, hence, Arundel is an exceptionally fortunate find. Even the next generation of astronomical telescopes will find it challenging to detect them. However, through the detective work of scientists, astronomers are beginning to understand how these elusive objects lived and died. Computer simulations show that tiny density fluctuations in the early universe played a role as the starting point for massive gas clouds. Without these variations in structure, nothing would have formed. The entire universe would have evolved into a homogeneous, increasingly thin cloud of hydrogen, helium, and a small amount of lithium. However, thanks to gravitational attraction, these fluctuations became gathering points, massive clouds where gas continued to accumulate. Eventually, these clouds collapsed. In doing so, they heated up to over 1,300 degrees Fahrenheit 700 degrees Celsius. This temperature is too high for a region forming stars in the modern era to give rise to stars. Indeed, if a cloud is hotter by about 10 Kelvin, 442 degrees Fahrenheit or 2.63 degrees Celsius, the speed of the atoms within it would be too fast for them to bond together and ultimately form stars. But the clouds in the early expanding universe were much larger and denser than the nebulae today. Among them, some hydrogen atoms paired up to become hydrogen molecules. Because molecules are better at emitting infrared heat radiation, the temperature dropped, and the clouds inside could contract further. Each region could be hundreds of times the size of the Sun. With such large masses and equivalent gravitational force, they could overcome external radiation pressure. These masses did not separate as they contracted, so only one star formed from each mass. The result is that the first stars likely had enormous sizes, estimated to be from tens of times the mass of the Sun to 1,000 times the mass of the Sun, and shown perhaps millions of times brighter than the Sun. Astronomers theorized that in addition to their large mass, the first stars were also extremely hot. Their surface temperatures could be 15 to 20 times that of the Sun, and most of their emitted radiation fell within the infrared region of the spectrum. Although supernovae did not play a direct role in the birth of the first stars, events like these are part of the causes leading to their demise. The larger a star is, the shorter its lifespan, so the first stars may have only existed for a few million years or less. Theory predicts that when a star with a mass between 140 and 260 times that of the Sun reaches the end of its life cycle, it will create an unstable pair instability supernova. In the core of such an object, electron-positron pairs disrupt the balance between outward radiation pressure and gravitational forces pulling inward. As gravity starts to dominate, the core will collapse. This causes its temperature to rise, leading to an enormous increase in nuclear heat. In fact, the star explosively blows itself apart without leaving any remnants, such as a black hole. In this way, all the elements synthesized by the star, including iron, expelled into space. This seeds the surrounding gas with matter, creating a mixture that will form the generations of stars in the future. Therefore, in a sense, the death of these stars is as crucial to the universe's development as their birth. Currently, scientists are searching for second-generation stars, focusing their efforts in the halo of the Milky Way, a region that includes old stars, and star clusters. Population 2 stars are concentrated in the core of our galaxy. Quilla is a red supergiant star that has existed for 3 billion years after the Big Bang. Quilla is also the first red supergiant star excavated from the early universe. Is a colossal glowing red space monster, a cosmic enigma from the early universe that the scientific team led by astronomer José Diego from the Cabrera Physics Institute believes could be a representative of red supergiant stars. According to S News, red supergiant stars are the evolutionary descendants of large stars with initial masses between 7 and 40 times that of the Sun. They are stars with the largest radii among all known star types, although not the most massive stars, as they are a celestial body that has been inflated. Stars, including our Sun, towards the end of their lives, will deplete their energy and expand into a new form known as a red supergiant, much larger in size than their original state. After a while, red supergiant stars will conclude their short-lived existence by collapsing into white dwarfs. Returning to the intriguing object mentioned earlier, the entity dubbed Q reveals its mysterious nature in the data from the James Webb Space Telescope, primarily operated by NASA with the support of ESA and CSA, the space agencies of Europe and Canada. The James Webb Telescope is currently the most advanced space telescope with exceptional observational capabilities. As a result, the red supergiant cosmic monster mentioned above, located at a staggering distance of 10.7 billion light-years, still falls within the lens of the James Webb Space Telescope. It resides in a massive ancient galaxy cluster known as El Gordo. The star may have collapsed and dissipated into the